Hi, my name is Susana Arellano. I'm going to be going over a fluids problem for my ME360 class with Professor Lehman, fall 2020. The problem has some important features highlighted. It states water is pumped from a large tank shown in diagram A below. The entrance to the pipe section is sharp-edged and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent, and the relationship between volumetric flow rate and actual head rise is provided in the pump specifications as shown in diagram B. Okay, we can see the relationship here. I will use h of A in the beginning, but I will put that they're equal to h of P. This is the same. It's head rise of the pump. It's equal to 20 minus 2,000 times the volumetric flow rate squared. In our first diagram, we see more pump specifications. We know we get the diameter and the height, the elevation. Okay, so I'm just going to start off by writing some variables down just to be easy to reference to. So given variables. First, we know we're using water from table, what table is it? There you go. From table 1.6, we know that density is going to be per meters cubed, 999, and the dynamic viscosity is going to be 1.2 times 10 to the negative 3 newtons times seconds over a meter squared, right? It says that we are using a large tank, so we labeled the state 1 and state 2. I labeled them this way instead of the other way, vice versa, because water is starting from this large tank and exiting through this exit over here through the pipe, right? So, right, says that the pipe section is sharp-edged. That tells us that the loss coefficient, K of L, is going to be 0.5. We get this from table figure 8.22. And then it tells us that the pipe is cast iron. So we get a roughness of 0.26 millimeters. This is from table 8.1. It tells us that the length, I labeled here, it's not in the original diagram, that the length is 2 meters. And it is fully turbulent flow. The problem asks us to determine the volumetric flow rate of the system to show that the observation of fully turbulent flow was correct, and to determine how much power must be supplied to the pump if the pump is 70% efficient. So we're also going to need to know, we're going to need our friction factor. I'm just going to solve for it right now so we can have it in the givens. Friction factor. We need to know the roughness over the diameter. We know that the diameter, oh, I'm reading backwards. Just gonna go. The diameter is given is 0.07, right? And then the elevation at 2 is going to be 0. That's where we're starting off from, so that the elevation of 1 is going to be, the difference is going to be 6 meters. Right, and then our head rise is equal to P, head rise of the pump, which is equal to 20 minus 2,000 volumetric flow rate squared. All right, and then to solve for the friction factor, we need the roughness over the diameter. This is, we already said, 0.26 millimeters over the diameter, which is 0.07 meters. This is 0.26 times 10 to the negative third. Meters cancels out because it's unitless. This gives us 0.0037. Right, and that is unitless. Because this is also fully turbulent, we can use these two factors to find the friction factor using the Moody diagram, which I will pull up right here now. All right, so our Roughness over diameter was very close to the 0.004. Just going to use this line for reference since it's a rough estimate, not an exact number. This wholly turbulent flow depicts when turbulent flow begins. Anything after this point, doesn't matter how high the Reynolds number gets, it's just going to stay fully turbulent. You can see from this diagram the very linear lines with no slope. Right, so following this line across here, all the way to the friction factor, we get around 0.028 for our friction factor. I'm just gonna put like the rough signs because this is not an exact. But there are other ways to find this. Just using the Moody diagram, the Moody chart is the easiest way I see. Right. Okay, now we can start working on part A, determine the volumetric flow rate. For this, we're gonna need our head loss equation with pump. Equation with pump. Right, this is kind of like Bernoulli's, just with head rise and head loss incorporated into it. It's the same, almost the same type of idea. I'm just gonna write it out. 2G elevation at 1 plus the actual head rise. In this case, I'm gonna put H of P instead of H of A is equal to pressure at 2, 2G elevation at 2 plus the head loss. Right, and then the head loss. The total head loss is equal to the major head loss plus the minor head loss, which we will work with later. Minor. All right. To simplify this equation that we have, we can refer back to our original diagram. We can see that both points at 1 and 2 are open to the atmosphere, so pressure will be 0. We can cancel these out. And our original problem statement states that water is pumped from a large tank. Because it is large, the area is large, and thus will have a really small velocity. We can we can say that it's negligible and equal to 0 in this case. Elevation at point 2 is 0, right? And this gives us an equation of, simplified equation of, elevation of 1 plus the head rise of the pump plus equal to, velocity of the pipe squared times 2 times gravity plus the head loss equation. Right, and what I'm gonna do is I'm gonna make everything in terms of Q and then solve for Q given our variables. Right, we know that this is equal to 20 minus 2000 times volumetric flow rate squared. V2 squared over 2G is going to equal to Q squared over area 2 squared times 2G, and this is because volumetric flow rate is equal to velocity times area, so velocity 2 is equal to Q over area 2. Right, just substituted that. Need another sheet of paper. Right, and then we just need to find our head loss, our minor head loss, and our major head loss. So for major losses, the friction factor is equal to friction factor times length over diameter times V2 squared over 2G. We can just substitute this into here because we already solved for that. It's going to be friction factor times length over diameter over times Q squared over A2 squared times 2G times gravity. Right, doing the same thing for minor losses. Okay. Minor losses, it's the loss coefficient times velocity squared over 2G. We'll make the same substitution we did before as well for this velocity. We're going to get loss coefficient times volumetric flow rate squared over area 2 squared times 2 times gravity. All right, and then adding these two together, we get, I'm gonna substitute the Q and the denominator out of here, just to make it easier later on. It's gonna be friction factor, length over diameter, plus the loss coefficient. Right, we can substitute all of these back into our original equation. Here we go, just gonna point these out. Go, all back into equation 1. Okay, this gives us elevation plus 20 minus 2000 squared, right, times 2g plus q squared over 8 2 squared times 2g friction. Okay, then solving for q, this is just algebra. Just don't think I need to really go into too much detail over here. Just moving everything to one side, substituting stuff out. 2g plus friction factor d plus 2000, just moving that to that side. Okay. Okay, gonna divide it by this whatever's in this parentheses, and then do the square root. Just gonna do it in one step to save some time. So 1 plus 20, 1 over a2 squared is equal to pi over 4d squared. Just gonna make that substitution right now so we don't have to solve for area. Pi over 4 d squared squared times 2 times gravity times 1 plus friction factor times length over diameter plus the loss coefficient plus 2000. Okay, now we can solve for 2. We already defined all of these variables. We're just plugging and solving. Volumetric flow rate is equal to 6 plus 20 over 1 over 4, 0.07 squared times 2, 9.81. The squared times 1 plus 0.028, 2 meters over 0.07 meters, 0.5 plus 2000. There you go. This will give us alright, this gives us 5.12 times 10 to the negative 2, or you can just move the decimals over, 0.05121 meters cubed per second. This is our volumetric flow rate. We're also going to need it for the next part as well. This is part A. Okay. All Alright, and then so going on to part B, it says show that the observation of fully turbulent flow was correct. Doing this, to do this, we need to understand Reynolds number and what determines laminar or turbulent flow. In theory, anything under Reynolds number of 2000 will give you laminar flow. If it's very similar, almost equal to, it's going to be transitional. And a Reynolds number over 2000 is turbulent. Right, so we just need to solve for Reynolds number. Reynolds number is equal to density times velocity times diameter over dynamic viscosity. We already found these variables in the beginning from table 1.6, and velocity is equal to volumetric flow rate over area. We just solved for this 0.05121 over pi over 4, 0.07 meters squared. Right. This is going to give us 99.05121 over pi over 4 squared 0.07. Right, this gives us a Reynolds number of 7.75 times 10 to the 5th. This is much greater than 2000, so we can say that this is turbulent flow, and it shows that our observation of fully turbulent flow was correct. Just gonna box this. This is our explanation why. Right, and then going on to part C, if the pump is 70% efficiency, we can put this in decimal form and say it's 0.7. Determine how much power must be supplied to the pump. Okay, we know that efficiency is power gained. In this case, power gained by the fluid over the power supplied. Okay. Right. This is going to be power of the fluid over the power supplied is actually the shaft work, the flow shaft work, right? Power gained by the fluid is density times gravity times volumetric flow rate times the head rise of the pump. Okay, we can solve for our shaft work, which is our power supplied. This will give us rho GQ HP over efficiency. Breaking this down, for 20 minus 2000 Q squared over efficiency. This will give us 9.81, 0.05121. 20 minus 2000, 0.05121 squared over 0.7. Shaft work B times 9.81. This gives us 1.057 times 10 to the 4th watts. We can turn this into kilowatts. So the power supplied is 10.50. If you round it, it's actually, here we go, 10.58 kilowatts. This is the power supplied to the pump. Right, that's pretty much it. And sign it off.